The next talk is on using navigation to improve recommendations in real time by Chao-Yuan, Christopher Alvino, Alex Smola, and Justin Basilico.
Hi, everyone. Today I'm going to talk about how to use navigation to improve recommendations in real time. And this is a joint work with Chris and Justin from Netflix, and also Alex Smola from Carnegie Mellon University. So the question we consider here is simple. So what contents to show to our users? So this is usually what we do. So we have some user history data. So for example, like clicks, play, rating, etc. And then we train some machine learning model, and then to predict how user will interact with this content. And then we present the page accordingly. But actually, it's actually pretty hard to predict user behaviors. So for example, people might watch different things when they are with different people. So if we are not able to make accurate predictions on these, how can we make accurate predictions on their behavior? And what's worse, so oftentimes we don't even know who's watching. So at Netflix, people might share accounts. So if we don't know who's watching, what content should we show? And their behavior can even depend on so many different random stuff. So for example, like their mood states, like how much time they have, etc. So for example, sometimes they may have time to watch a full movie. Sometimes they have only 30 minutes to watch a TV series. So in other words, the challenge here is user intention depends on so many factors that are hard to predict beforehand. And also, even for the same user, their sessions can vary significantly across sessions. And this violates our model assumption that user has some static states that we can estimate. So usually, this is addressed by using some context information. So for example, like time of day, day of week, location, device, etc. But this is just like giving us some hints about how to guess and give us some prior knowledges. But it doesn't really solve the problem. So oftentimes, ended up the system just present a mixture. So like put some action movies here, comedies there, and hope that one of them will work. So can we do better here? So how can we understand user intentions better? So we realize there's very rich information in their navigation signals. So for example, so when the users browse on the page, they might scroll on a roll, they might skip some content, they might read some information about a video, etc. And these actions give us very rich information about what they are looking for. So what we propose is the following. So can we observe just a few navigation signals, so for example, just from the first few rows, and then to improve the recommendations to the unseen part of the page. So in other words, this gives the following framework. So that is an online adaptation framework. So we assume that there's an offline system that generates a page, and then while the users are navigating on the page, and we use the navigation signal to improve our page in real time. So this framework is completely general. It can be applied to cases when the contents don't fit in the page, no matter it's a web browser or cell phone, etc. And I think in most cases, this is the case. Here we focus on one special case at Netflix. So we focus on sessions from Netflix PS3 user interfaces. So in this interface, contents are organized in rows, and then users can either horizontally scroll within a row to browse more videos, or they can scroll vertically to see other rows. And here we only consider scrolls as navigation signal in our experiment, but while in principle, you can use other navigation signals as well. And also here, we only consider reordering rows instead of shuffling the whole page. So let's talk about the model and algorithm. So on a very high level, our algorithm works like this. So for given a page of rows like this, assume we have videos organized in these rows, and then we assume that a user is only interested in a subset of rows. And then we introduce a latent binary variable to indicate whether this user is interested in this row or not. And then we assume that a user will only scroll or play from the rows that they are interested in. And they don't scroll or play from the row they are not interested in. So what's happening is like something like this. So given an initial page, and then the user come and interact the page, and then we use this to update our estimation of their interest. And then we use this updated results to rearrange the page. And if we look at the graphic model, it looks like this. So the important parts are the two plates, the two inner plates. So the green plate is the rows. And within each row, the blue plate is the videos. And so for each row, we have an interest variable and also an observed variable to see whether there's a horizontal scroll or not. And for each video, we have a variable controlling the play behavior. So during online adaptation, what's happening is we observe more data scroll, and then we use this new data to update our posterior estimation of the session-specific parameters. And this, in turn, then will update our estimation of their interest. And then with this updated interest, it will, in turn, change our marginal probability of play for each video. And we can then use this updated estimation to present our page. But of course, just using online signal cannot give good recommendations. So we still need some offline parts to estimate the long-term behaviors. So in our paper, we show that this can be achieved by some efficient EM algorithm. And in experiments, we can optimize this with efficient SGD, stochastic gradient descent. So a few comments about this model. So first of all, the choice of model can be largely independent of function class. So that is, you can use any emission model you like. So for example, you can use decision trees, inner product, factorization machine, etc. All of them can be used in this framework. In our experiments, we use some submodular formulations to capture some diminishing return effects. And on the other hand, this model is tightly coupled with the UI design because we need to encode the way that users interact with the system in some quantifiable terms. So it is tightly coupled with the specific UI interface. So one potential problem with this approach is that it adds some latency because there's additional round trips. So we propose to do some prefetching. So that is, we prefetch a larger amount of data to our browser. So while during the session, we can do all the updates within the browser. And this will not add additional latencies online. So experiments. So we tested this framework on a real data set from Netflix, Netflix PS3 sessions. So we trained on 2 months of data, and then tested on 1 month afterwards. And in the pages, we prefetch 40 rows of data, 40 rows of pre-computed rows. And then for each row, there's no more than 75 videos. So let's first of all look at some properties of this data set. So here the horizontal axis are how far the user scrolls on a row. So we see that as the user scrolls more on a row, the conditional probability of playing a video is much higher. So this also confirms our choice of using scrolls as navigation signal. And to evaluate online adaptation, this is how we do. So we fix 10 rows on the page, and then we perform update, and then rearrange the rows after that. And we evaluate this with MRR and also precision at 5. And we also compare with the baseline of factorization machine. So what we see is that online adaptation actually helps our recommendations a lot. So we see that the more interactions we observe on the page, we are able to improve our recommendations more. And interestingly, we see that even with only interactions from 2 rows, we are already able to observe significant improvement. And more interestingly, this approach also helps us to address the cold start problems. Because as we see that for users that has no trending data at all, this framework actually improves the most. So this also means that with this, we are able to provide some personalized recommendations, even this user is totally new. And in our paper, we also talk about some suggestions how to model play probability accurately. So first of all, it's important to model impression fatigue. So on the left figure, we see that the more times you show a video to a user, the less likely they will play from the video. And know that the Y scale is log scale. So this effect is actually stronger than exponential. So it's really important to model this. And also, it's also important to model repeated plays. So for episodic titles, it's not very surprising, right? So for example, like TV series, it's not surprising that the user will keep watching. But what we observe is, even for standalone titles, for example, like movies, people also tend to watch the same movie again, and again. So it's important to also consider this. And in our experiments, we found that with modeling these effects can improve our performance even more. So in conclusion, in this paper, we talk about a new framework about like how to use navigation to improve recommendations in real time. And also it helps with cold start problems. And we also propose to use efficient prefetching so that all the computations are in the browser, so no latency are added. And we also discuss how the importance of modeling impression fatigue and repeat plays in order to accurately model play predictions. And it's a general framework, so this can be applied to a wide range of user interfaces. Thank you.
Thanks for the great talk. Do we have any questions? One up there. Oh, another one there. Quite a few questions here.
Okay.
Go ahead, Peter.
Excellent. Left to right.
Can you stand up?
I'm Peter Brusilovsky, University of Pittsburgh. Thank you for a very nice talk. I'm specifically excited that the recommender system community just rediscovered adaptive hypermedia, where all modeling is actually done by observing user navigation. But it's done on a completely new level, which is really exciting. So the question is, I'm trying to figure it out from your algorithmics. I'm not sure to what extent what you learned from user browsing is used for user alone, or it could be trickled down to help the other users. So what I learned from me can help others. Could you clarify that part?
You mean how the interactions from other users help us?
No, vice versa. So you learn about my browsing, right? It helps me. It helps to learn my model, and it helps to recommend for me good things. Now, to what extent what you learned from me, from my browsing, might help recommending good things to other people? Collaborative filtering is all about that, right? What you learn from others helps me. But that seems so far just like pure kind of content-based. It's not helping anyone else but me to observe my browsing. Am I right or I'm wrong? I'm just trying to figure it out.
I see. Let's see. So, yes, so I think this will help because what we're doing is updating the possession parameters. And on the other hand, the possession parameters interact with item latent factors. So by observing your interactions, it helps us update the item latent factors. So in that sense, it's still a collaborative filtering framework. Thank you.
We had another question up there.
Hi, I'm Mario Schiminacci from ContentWise. Great talk. Actually, I found very interesting the fact you use navigation to influence the ratings of the items and everything else. Have you already think about to include other signal of intent, like a user that prefer to perform a search instead actually scroll the page? And actually, how you can integrate this kind of signal in your model?
Do you mean by using searches?
No, I mean a signal that a user don't like what you are presenting in the page. Maybe just the user go in the search box and perform a search. Have you think about how to integrate this kind of implicit signal in your model?
I see. So that part is not explicitly modeled now in our model, but I think it's certainly possible to devise some better emission models to model more signals jointly.
Any more questions? Michael?
Michael Strand, Boise State University. Very good talk. Question about the reliability of these navigation signals as markers of intent. Because it seems that scrolling particularly is going to be a really noisy signal. I mean, maybe I look for something to watch, but maybe I come in, I want to watch the next episode of Bones, something catches my eye, so I see, oh, do I want to add something to my list? And then I go watch Bones. So how reliable is this scrolling as a signal of overall intent, maybe versus short-term intent? And also, do you have any insight on how the reliability of scrolling as an intent signal changes across client platforms from mobile to set-top box to desktop?
Okay, thank you. So first of all, in this paper, we focus on only one user interface, but in the future, we might explore on other interfaces as well. And and also the navigation signal. So yes, it is very noisy. It can be very noisy, but we believe that there's signals in there. So I think it's possible to devise some better noise model or to use multiple sources of navigation to overcome this. But we believe that since there's signals there, and so it's better to use them.
Thanks for the great talk. I had one question. How well do you think you can incorporate negative feedback and let the model reset? For example, when you start exploring something and you realize you don't want to go there anymore and want to start from scratch.
You mean sometimes people might scroll something and then realize this is not what they want.
Right.
So in our model, we didn't explicitly say that the more scroll, the more something, but just we provide some dependency relationship and let the model to figure this out. So I think if many users are behaving like that, it's possible for the model to figure this out.
Okay, any more questions? So let's thank the speaker again.
Thank you.
Great talk.